All right, hi everyone. So today's mini lesson is going to be talking all about dilations and scale factors. And so when we're talking about dilations, we're thinking about the enlarging or the shrinking of some kind of geometric figure. So I want to start us thinking about what dilation means by looking at this picture of LeBron. So the original picture is this one here on the left with no circle on it. This is the original photo of LeBron. But I want y'all to look here at this second photo of LeBron on the bottom. Now the one on the bottom looks distorted. Some things you might notice is that his head looks like it's flattened out. His shoulders have gotten super wide. You might also notice that his whole body looks shorter. And the reason why that is we haven't shrunk the horizontal side and the vertical side by the same amount. We've made the picture shorter, but we've actually also made it wider. So we haven't done the exact same thing on both sides of the photo. Whereas in the picture on the top, what we've done is we've made it shorter and we've also made it narrower. And so the same thing we've done to one side of the picture, we've also done to the other side of the picture. And that tells me that this photo, the photo on top, is a dilation of the original photo, whereas the photo on the bottom is not a dilation of the original photo. So now I'll give you the actual geometric definition of a dilation. So reading this, a dilation with center O and positive scale factor R takes a point P along the ray OP to another point whose distance is R times farther away from O than P is. If R is less than 1, then the new point is really closer to O, not farther away. And so this gave us a lot of technical details, but I want to take this and break it down into some terms that we can understand. So first things first, a dilation just means that we are making it proportionally bigger or smaller. So we're making the shape proportionally bigger or smaller. Scale factor refers to that quantity that tells us exactly how much smaller or bigger to make it. So with our scale factor, what we want to do is multiply that by the original length to give us the new length. So the scale factor R is that number that we're going to be multiplying the sides of the shape by. And then the last thing that this definition tells us is that if R is less than 1, then the new point is going to be closer to O. That means it's shrinking. Whereas if R is greater than 1, then the new point is going to be farther away. The shape is getting bigger. And so I'm going to put up some notes for you on my whiteboard to help y'all break down this definition some more. So I'll start by defining dilation. We said that dilation is making the shape proportionally bigger or smaller. Scale factor is the number we multiply by to change the size. And we use the letter R to denote the scale factor. And so, if our scale factor is less than 1, the shape gets bigger. I'm sorry, if R is less than 1, the shape gets smaller. If R is equal to 1, the shape stays exactly the same size because anything multiplied by 1 is itself. And if R is bigger than 1, then the shape gets bigger because when we multiply something by a number bigger than 1, the number gets bigger. So I'm holding up these notes, and I'll give y'all a second to copy them down. Feel free to pause this video to get those notes down. And now I'm going to go ahead and move on to giving you guys an example. So let's say we had a line segment called AB that was 10 centimeters long. So I'm drawing this line segment AB that's 10 centimeters long. It looks like this. And so what if I wanted to dilate this with a scale factor of 2? So R equals 2. If the scale factor is 2, that means that the line segment must be getting longer because 2 is greater than 1. And so now I'm going to draw something, and I'm going to call it A prime B prime, just like this. That apostrophe we read as prime, and that tells us that this is our dilation. When you see that symbol, that means we've created a dilation. And so now I'm going to say our scale factor is 2, so we multiply 10 times 2, and we get that the new length is 20 centimeters. Now, what if I wanted to use a scale factor of 1/2? In that case, this tells us that our line segment should be getting shorter because 1/2 is smaller than 1. And when our scale factor is smaller than 1, our shape has to get smaller. And so now I do the exact same thing I did with this first line. I take the original length, 10, I multiply it by the scale factor, and I get the new length. And so now I have a new line. I'm going to call this A prime B prime because it's also a dilation. So I have R equals 1/2, and what I have is 10. Let me tilt this down so you can see it better. 10 times 1/2. When I'm multiplying a fraction like this, it's the same as having 10 over 1, and you just multiply straight across the top and the bottom. So I get 10 times 1 is 10. And then on the bottom, 1 times 2 is 2. And 10 divided by 2 is just 5. And so what I end up with is that when I have a scale factor of 1/2, the line segment is now 5 centimeters long. So as you can see, when our scale factor was bigger than 1, our line segment got longer. When our scale factor was smaller than 1, our line segment got shorter. And we found the exact length by taking the original length and multiplying it by whatever scale factor we got in that question. And so we're going to take this one step further now and see if we could do this with a whole shape. So let's say I had this shape right here, a rectangle. I'm going to call this rectangle ABCD, where the short side is 1 and the long side is 2. So this is my rectangle ABCD. And let's say I want to dilate ABCD with a scale factor of 3. And remember what we do in a dilation. We have to multiply every side by the exact same scale factor. So if our scale factor is 3, I've got to take 3 and multiply it by every side of this rectangle. So in a rectangle, remember that the long sides are the same length as each other, and the short sides are also the same length as each other. So I'm multiplying all of these by 3. And when I do that, I end up with something that's going to look a little bit like this. I'm going to call it A prime, B prime, C prime, D prime, labeling it just like I did before, putting that little apostrophe right after. And I'm multiplying each of these by 3. And I end up with the long sides are equal to 6, and the short sides are equal to 3. And you see, what we did is we just multiplied each of those sides by our scale factor to get the new lengths. And so you'll notice the key thing is we've got to keep all those proportions the same by multiplying all the sides by the same scale factor. So that tells us one of the key factors of a dilation. But the other thing you have to notice is in a rectangle, all the angles are 90 degrees. This is a 90-degree angle, this is a 90-degree angle, this is a 90-degree angle, and this is a 90-degree angle. And you'll notice that in the new rectangle we drew, these are all still right angles. The same is still true for our new rectangle. And so what I just went over are the two key properties of dilations. The first is that all the corresponding angles are congruent. Angle A was equal to angle A prime, excuse me. Angle B was equal to angle B prime, and angle C was equal to angle C prime. So all corresponding angles are congruent. Dilation might change the length of the sides, but it doesn't change the size of the angles. And the second key property is that all sides are multiplied by the same scale factor. If you're multiplying one side of the triangle or the rectangle or the rhombus or whatever shape, if you're multiplying one side by 2, you've got to also be multiplying all the sides by 2. So all sides are multiplied by the same scale factor. So I'm writing this out on the whiteboard. I'll hold it up to the camera in just 1 second. And so these are those two key properties of dilations that we need to remember. And these can help us solve any kinds of questions about dilations and about scale factors in the future. So just remember, dilation means we're stretching or shrinking a shape. We're not changing what shape it is, we're just changing what size it is. And as long as you remember that anytime the scale factor is bigger than 1, the shape gets bigger. Anytime it's smaller than 1, the shape gets smaller. And anytime the scale factor is equal to 1, the shape is going to stay the same.